So we'll need to discuss the photoelectric effect. And this was the second issue that scientists had issues with at the end of the 19th century. And basically, the photoelectric effect was a phenomenon that was first discovered by Heinrich Hertz. And basically, what we basically had is a vacuum tube. And we basically had incident electromagnetic waves onto this metal, which we'll call a cathode. And what we noted was that, well, depending on the frequency and so on, we noted that there would be electrons moving across. And basically, current, remember, is a flow of charge. And we basically called this the photocurrent because it depended on the incoming, radiation. So basically, the photocurrent is the current due to incident radiation. All right. Now, this like blackbody radiation, this experiment caused problems for scientists for exactly the same reason that that blackbody radiation caused problems. When I say exactly the same reason, what I mean is the experiment results do not conform to what theory said. All right. So we've got experimental results, and we have theory, and they didn't match. So basically, when we did this experiment, we get our results. And what we basically found were a few sort of, phenomena, all right? So we found that the photocurrent, which is basically how many electrons kind of went out, was not affected. Well, how should I, let's put it this way. So the photocurrent is limited by the intensity of the light. So, for a particular intensity for intensity, think of that as brightness. So for a particular light that is, certainly amount of brightness, that gives you a certain amount of current, okay? But importantly, it did not affect the energy of the electrons. All right. And theory would say it should affect the Ke max. All right. But, well, it doesn't. Now, we also found that as the frequency increased, then we found that the intensity was unchanged. So if we keep, as we increase frequency without changing frequency, what we found is that the photocurrent didn't change. But Ke max was affected. And again, that's not what we expected. So perhaps it might be better shown here. So, change in variable, experiment result, theoretical expectation. So what we found was that if we increase the intensity, The experimental result was that the photocurrent increased and Ke max unchanged. Well, we were expecting, based on our theory, that Ke max would go up. And the photocurrent, well, probably wouldn't really increase. But the key thing was we expected Ke max to go up. And obviously, if it goes down, then that goes down and so on. Now, we also found that as we increased frequency, our experimental result was Ke max went up and photocurrent unchanged. But what we expected was that, well, the Ke max would be unchanged. And we measure Ke max by, using V stop. So V stop goes up. If we make frequency go down, and this one is worth writing for reasons you'll see quite clearly, you'll see that the Ke max will go down until 0. But once Ke max reaches 0, then your photocurrent equals 0. If, the frequency is less than some threshold frequency. And there is no photocurrent, irrespective, no matter of the intensity or duration of the radiation. So what we're saying is, if the frequency is, if you drop the frequency, you'll notice that the Ke max goes down. But if you go down far enough to a F0, which is called a threshold frequency, then no matter how bright that light is, no matter how long you shine that light on the surface, you just don't get anything. It doesn't matter. Now, the theoretical expectation is there should be no threshold frequency. In other words, even for low frequencies, you should still get a photocurrent, even if it takes a long time, or you need a very bright light, etc. So, the experiment is saying that it doesn't matter. It doesn't matter how bright the light is. It doesn't matter if you shine it on for, like 1 second or an hour or anything. You don't get it. The theory should say that, well, it shouldn't matter. I could reduce the frequency to a low enough level, a very low level, but as long as I keep shining that light and do it for long and hard enough, well, then I'm still going to get a photocurrent. It might be low, but I'll get one, is what they're saying. And clearly that doesn't match up with, what we're saying so far. All right. And so those are really the sort of key things here. And what we have, of course, is the inability to explain this. Now, it might we'll kind of just sort of explain about what we're saying happens. We're saying light comes in. It basically gives energy and knocks out an electron. Now, this electron will have kinetic energy. So this electron had to kind of pay a get out of jail free card. So think of this as jail, right? So it had to pay a get out of jail free card. They had to, pay and bribe the guards or something to get out of jail, right? So it's out of jail now, but it might have money left over. And that's your kinetic energy, all right? So it might have energy left over. So basically, what we're saying is, the light has energy. It gives it to the electron. The electron then uses it to escape. It pays a fee. and it might have sort of leftover energy. All right. So that's kind of the gist that we've got here. And so when we're talking about Ke max, so one thing you might want to understand is not every electron will have the same amount of leftover energy because, you know, they might have spent that money differently kind of thing. So we're trying to calculate, when we calculate Ke max, we're calculating the maximum Ke of the electrons. So basically looking at the electron who has, you know, kept the most money after they've paid the fee. All right. And we measure that by measuring this voltage. So we use, you know, voltage stop to basically measure Ke max. And we do that by making this voltage variable. And so you need to know, because you could be tested on this, how we would connect this. And you would need to recognize that we would connect the negative to this side and the positive to this side. And we do that because what we're basically doing is, okay, the electron is knocked out and it wants to go to the right. And because we want to know how much the electron wants to go to the right, we make it harder to go to the right by making this negative to repel it. Okay. And basically, you know, when we're doing stopping voltage, the more negative we make it, the harder it is for the electron. And we adjust it until, well, you know, it gets as hard as you possibly can just before they all stop. Well, you know, that's why I call it the stopping voltage, right? And this, by the way, relies on the fact that QV, which is your work, must equal, you know, half mv squared. So if we can work, we know the charge of an electron. We know the voltage because we found it using stopping voltage. And that's the amount of work that is required to stop, you know, all the electrons, including the toughest one. And therefore, that will equal the maximum Ke of the electron. In case there's any confusion, this here is voltage, and we would use stopping voltage. This here is velocity, if you are asked to calculate the velocity, which I don't think you normally would be, but, you know, it does relate to your, you know, dynamics course in year 11. So that's the link between sort of stopping voltage and, you know, your kinetic energy max. Now, when your electron sort of pays a fee to escape, we're basically saying that, you know, you need energy to leave the metal, and that we call the work function, which is sometimes represented by W and sometimes represented by delta phi. I'll use phi here. And so you need to understand how to explain this. And basically this is explained using Einstein's sort of particle model of light. So basically Einstein used Planck's idea that energy is quantized. And that the, you know, E equals HF, where E is the energy of a photon. And where a photon is, you know, basically a particle of light. So basically, you know, Einstein came up with a model where it says, okay, stop thinking about light as a wave. Think of it as a stream of sort of particles, lots and lots of particles that are coming in. And basically these particles each have energy, which we can calculate using Planck's formula, E equals HF. And these particles, you know, impart energy. So you can either, you know, the particles can transfer the energy, and it's an all or nothing process, right? So you can either, you know, think of it like a collision. You're basically, we're passing all the energy to the other thing, or we just pass through, you know, without interacting. So, you know, you can't choose to give half your energy away. You're either going to give it away or you're not. And so particles can transfer the energy, but it's done sort of in a quantum manner and discretely. And I guess in classical physics, you'd say that, okay, you know, yes, the light might not have enough energy to knock the electron out, but if I keep giving you light, then it's a bit like, okay, I don't have enough money today, but I received 1 cent. Tomorrow I'll receive another cent. And the day after I'll receive another cent. So, you know, the classical theory would say it doesn't matter how much money you receive every day, even if it's like 1/10 of a cent, whether it's $1 a day or a cent a day or, you know, $500 a day, you know, there's no minimum, right? If you assume that you can keep that money and just save it up, then you might need to wait a million years, but you can buy whatever it is you want to buy. So, you know, the work function is a cost, and that cost doesn't seem to go up. And so we're basically saying if you save up enough, you should be able to go. But what we're saying is, well, no, you're not allowed to save. You either grab the money and spend it now, or you can't grab it at all. And that would explain the contradiction here, right? About this. And under classical physics, basically energy was related to amplitude under year 11 wave theory model. You don't really do wave energy much in year 11, but basically the intensity is a measure of amplitude, and the amplitude squared, it relates to energy. And that's why classical physics thought that would increase the energy. But, well, our experiment shows it doesn't. So what basically Einstein said is, okay, we'll just use E equals HF. And because as E equals HF, as frequency goes up, energy goes up, which of course means your KE max goes up. Simple enough. So he can explain why K max goes up. At least using his model, we can sort of explain why K max would go up as, you know, frequency goes up. And then the next thing you need to explore is intensity. And he basically said, think of intensity as basically more particles per second. So, you know, it's just intensity is the number of particles per second. And so if you like, think of it like, you know, ping pong balls, right? If I have small number of ping pong balls versus a large number of ping pong balls, small number of ping pong balls is low intensity. High number of ping pong balls is high intensity. But basically we're saying kind of like, you know, intensity is different to sort of, you know, energy. So, you know, we've got low energy and high energy, and we've got sort of low intensity and high intensity. So intensity we're basically saying is just your rate. So for example, you've got, you know, 10 balls per second, 10 per second. And this is 10 per second. And a high could be, you know, 10,000 per second and 10,000 per second. All right. So that's low intensity and that's high intensity. But you could have 10 ping pong balls per second, or 10, you know, or 100,000 or 10,000 ping pong balls per second, but they're still ping pong balls, right? Whereas you could, for example, have 10 tank shells per second or 10,000 tank shells per second. So, you know, Einstein's basically saying, yeah, well, you know, you've got low and high intensity, and just think of that as the number of sort of, you know, balls a second. But that's not, you know, that's just intensity. That doesn't measure the energy level, right? So if you think about it, if you have a tank, you know, if you throw a ping pong ball at it, tank's not really going to care. You know, you throw 10 ping pong balls at it, still not really going to care. You can throw 1,000,000 ping pong balls at it, it still doesn't really care. I mean, it's just going to bounce back, right? It's not going to do anything. And that's exactly what we're saying. If you don't hit it with a, you know, if you don't hit it with a photon that is going to knock the electron out, nothing's going to happen. And that's why you're going to have a threshold frequency over here. You need a minimum amount of energy to knock that electron out. And if you don't make it, you just don't make it and nothing happens. It doesn't matter if you keep hitting it, but you need to make that threshold. Doesn't matter if you throw a million ping pong balls at a tank, it's just not going to do anything. On the other hand, if you fire a tank shell at it, and let's just assume the tank shell destroys the tank, well then, the more tank shells you fire, the more tanks you destroy, right? And that's why, since, that's why intensity doesn't have anything to do with the number of tanks you destroy, right? Because, frequency doesn't have anything to do with the number of tanks you destroy. You could fire a very small tank shell or a big tank shell, but let's say they both do the job. Every tank shell is only going to knock out one tank, just like every photon will only knock out one electron. Doesn't matter how big or good that shell is, one shell, one tank. One photon, one electron. But if you fire lots of shells and they're all good enough, then you're going to knock out lots of tanks. That's why if you fire lots of shells, high intensity, you're going to destroy lots of tanks, or you'll release lots of electrons, which is photocurrent. And that's why we would say intensity is particles per second, and therefore, each photon knocks out one electron, and therefore, as intensity goes up, photocurrent goes up. So that's basically the idea there. Now, you will very much need to know your graphs. So pay attention to your graphs. I'm going to assume your graphs here are Ke max in joules and your frequency. So when you draw this, you should expect to get straight lines. And this x-axis will represent, threshold frequency. So technically the line, only starts from here, and this is a dotted line, but we kind of draw it further until it hits a negative axis. So this will be like negative, phi. So this is a work function. So basically, as frequency goes up, K max goes up. So it's an upward sloping line. Okay. Using Einstein's theory, we're saying that the energy of the photon, which is equal to HF, must equal basically the work function plus your Ke max. So rearrange to get Ke max, you're going to get equals HF minus phi. And basically, you can think of this as, y equals mx plus b. And that's why your m will equal h, your b will equal negative phi. And that's why this is negative phi. And that's why your gradient will equal Planck's constant. Now, for the same reason, that's why you can kind of, algebraically manipulate it and get phi is going to be equal to h times f0 as well. All right. So those are relationships you should know. Now, you should pay very special attention to the fact that I've said already that this is in joules and this is in hertz. Now, do be careful with that, because you might get very similar graphs where Ke max is not in joules and it's in EV, for example. Or you might not get K max on the vertical axis at all. You might get V stop in volts on the vertical axis. And in those cases, then obviously the gradient is no longer Planck's constant, because you've changed things. The graph will still look like this, but you'll still have a threshold frequency there, but that's no longer the work function. As a number, it's no longer the work function, and the gradient as a number is no longer the Planck's constant. So be careful with that. If it's Ke max but in a different unit, just convert the unit. Easy enough. If they give it to you as voltage stop, not Ke max, then you just need to convert it to Ke. So remember, the relationship is Ke max equals QV. So if they've given it to you in terms of V, you just need to multiply all those values by Q, which is 1.602 times 10 to the negative 19 to convert it. That's it. But, you know, lots of students, I suppose, didn't pay attention to that. All right. Now, the other thing you'll kind of need to note is the sort of what happens if you use a different metal. So if you have a different metal, nothing changes at all, except for the fact that you have a different work function because it takes a different amount of energy to escape from that metal. So just shift this up or down accordingly. So, you know, if that's one metal, then the next metal would be, you know, looking like this, right? So you'll have its, you know, work function and its threshold frequency, but, you know, it will still have a Planck's constant, which is the same, and all the sort of theory will still be the same. And, you know, and that could kind of go both ways, right? You could go one that, you know, does this. But the point is they should all be parallel. Okay. And that should that should hopefully cover everything you need to know about photoelectric effect. So the next things we will talk about with special relativity, and we can go through this hopefully relatively quickly because it's, you know, it could be hard to understand the first time you do it, but you've all done this by now, so hopefully it's not too hard. So special relativity is one of two theories of relativity of Einstein. And Einstein basically came up with the special theory of relativity, which is the one you study. And basically what we're saying here is that he has a postulate after his thought experiments, and basically there are two things that underpin his special theory of relativity, and that is that the speed of light is constant. And so basically that says that the speed of light is constant for all inertial frames of reference. And of course, the other is that all inertial frames of reference are equivalent. Now, I can prove these things, you know, the things that follow from this mathematically, but let me just be clear, and I think some students don't understand this part. So when we say the speed of light is constant, we don't mean that it's just, you know, okay, the speed of light is 3 times 10 to the 8, and, you know, it's just a number. What we're saying when we're saying the constancy of the speed of light is that if you're person A, you know, looking at this light beam, and, you know, you're going to the right at, you know, 100 kilometers per hour, and, you know, you're person B going this way at 100 kilometers per hour, you know, we've done relative velocity in year 11, right? And you know that, okay, so if you're both relative to the ground and C is relative to the ground, you would say the velocity of A relative to B is, you know, 200 kilometers out to the right. And you do that by using, you know, VB minus VA kind of thing. VA minus VB, I mean. And that's why I get 200 kilometers per hour to the right. But we're not saying, okay, you know, speed of light is just some number 3 times 10 to the 8 in that way. What we're saying is that no matter who looks at light, we're saying the velocity of light relative to A is C. The velocity of light relative to B is C. Even though A is going to the right and B is going to the left, when they both look at a light ray passing by, they both see it as going as at 3 times 10 to the power of 8. That is what we mean by that postulate. Not that that light speed doesn't change, which, you know, is also what we're saying, but more that it's not relative to how you move. Velocity of light is the constant, you know, whereas, you know, you can move any direction you want, as much as you want, but when you look at a light beam, it will always appear to move at 3 times 10 to the power of 8, even if, you know, we change these numbers to, you know, 100,000 meters per second, and this is 100,000, you know, meters per second, it still doesn't change. All right? That's what we mean by the speed of constancy of the speed of light. I can make these numbers really big, so it's closer to the speed of light. We're not just going, oh, it looks like c because it's close, and c is so big and we're going so slow. Even if I make this number really big, we're saying we still see that as c. And that's what we mean by this constancy of the speed of light thing. All right. So once we have the constancy of the speed of light and the fact that all inertial frames are equivalent, then we will have some very counterintuitive effects. So we'll have effects that might not seem normal to you based on, everyday experiences. And we call these relativistic effects. Relativistic because they relate to relativity. Relativity because they relate to your velocity. And so typically we usually ignore them because they're so small if the velocity is less than 0.1 c. And the effects that you basically need to think about are time dilation, length contraction, and relativistic momentum. There's also a formula that you don't need to know, but basically it helps you work out relativistic velocity. So, there's a formula that helps us work out how the sort of velocity is relative to each other when you're talking about relativistic effects. And that will help you explain, but you don't need to know it, why everything looks at light at the speed of light. Now, you'll just need to be very clear when you're doing these questions about what each thing means. So the formulas are there all in a reference sheet. Now, basically, your t is, the time that you're seeing in one reference frame. And the t0 is the time in the rest frame. So basically, whoever is not moving relative to that time period. So, if you've got someone in a spaceship who thinks that, as far as they're concerned, 5 hours have passed, then that means t0 for the person in the spaceship is 5 hours. Whereas t is the person, for example, on Earth looking at the spaceship. And we're saying the person on the spaceship thinks 5 hours have passed, but the person on Earth will think a different amount of time has passed based on the velocity that the spaceship is traveling at. Okay. And this whole thing here is just your, factor. It's just a factor. In other books, you often see that as gamma, but basically it's just a factor. So when you divide by this factor, the time gets bigger. That's why it's called time dilation. And length contraction basically gives you L equals L0 times the square root of 1 minus v squared over c squared. And this time you'll still get a factor. So this is still gamma. And hopefully you guys can see that, as velocity gets bigger, this fraction gets bigger until, c, you can't get bigger than c. So this fraction gets bigger, but smaller than 1. So this number in the denominator gets smaller, gets bigger, I mean. So the square root gets bigger. Okay, let me start again. As v gets bigger, v squared over c squared gets bigger. So 1 minus v squared over c squared gets smaller. So the denominator as a whole gets smaller, which means when you divide by a smaller number, your t will get bigger. So note, as your velocity goes up, square root of 1 minus v squared over c squared will go down, which results in t going up, and it results in L going down. Okay, so your relativistic momentum is then going to be, well, P is basically going to equal, well, mv. So your P equals mv, but it's going to be, again, divided by 1 minus the square root of v squared over c squared. And those are your relativistic effects. Now, you'll need to then basically use these. So then basically also you need to understand that there's evidence for these. There's quite a lot of evidence, but the key evidence you need to know about are basically talking about sort of, you can look these up, but basically it's the cosmic muons from Earth's surface. And basically the idea is the muons have a half-life and they kind of decay very quickly. They kind of, think of it as, you know, they're short-lived. And so they shouldn't be able to get to Earth's surface, but they do get there. And so I guess we think of it then as, well, if they can't get there, but they do get there, then they're measuring their half-life. So we're measuring the time and they're measuring the time. And to us, that time has become longer. So they should have, you know, decayed, you know, died off, if you like, but they haven't, you know, their lifetime became longer because they're moving so fast. And we're measuring the time. And we would explain it as, well, their lifetime didn't become longer to them, but when we measure the time, it became longer to us. Okay. And we would explain it from their point of view as, well, they would say they're just as short-lived, but as far as they're concerned, they never traveled that far. They just traveled a shorter time, you know, shorter distance. So that's one way. Another way is to use the atomic clocks. So, you know, remember Einstein came up with this theory back in, like, you know, 1905. So, you know, this is before planes, and most certainly before, like, you know, nuclear bombs and nuclear energy. So we didn't have atomic clocks back then when he came up with this theory. But the thing with atomic clocks is that they're very accurate. You know, that's how we basically keep time nowadays. It's the most accurate way we've got to keep time. And it can measure time extremely accurately. And so, you know, if you might not tell a difference because at sort of low speeds, an atomic clock might be able to. And so most certainly can when we fly at high speeds. Well, by high, I mean like fighter jet speeds. So still quite low by speed of light standards, but high enough. So what we basically did was we put a few clocks on a fighter jet and put a few clocks on the ground and, you know, flew some clocks around a bit and came back and measured to see if there was a time difference. And obviously for anyone who uses a normal stopwatch, they'd be like, what are you talking about? But if you're using an atomic clock, because it measures so accurately, you can actually tell the time difference. And more importantly than telling there is a time difference is noting that it, you know, follows our formula. And all the clocks on the plane slowed, you know, slowed down, and all the clocks, you know, on the ground basically went faster, is the short version. And so basically we've, you know, proven that. That's another sort of way. And there are also ones from sort of particle accelerators, as well as cosmological studies. So you'll need to know some of the, you know, those evidence in case you get asked an extended response on that. But I will leave you to look those up because we do need to quickly get on to module 8. Now, as part of his theory, he also has what's called the mass energy equivalence. Where we've got E equals mc squared. All right. And so what we're basically saying is that the mass is equivalent to energy and this can be sort of converted through a conversion factor of c squared. So remember c is 3 times 10 to the power of 8. So c squared will be like 9 times 10 to the power of 9. So quite big, not 9, what am I writing? 16. So we're basically saying that a tiny amount of mass is equivalent to, well, you know, using the same numbers, a lot of energy. Okay. And basically we're saying that's the case when we talk about, you know, in module 8, sun's, you know, releasing energy in terms of sort of fossil fuels, sorry, nuclear fusion, I mean. It also applies to sort of, you know, nuclear bombs or power plants. And that's a nuclear sort of fission. And it also, of course, applies to just, you know, the most simple case of annihilation. So that's when you have a particle plus an antiparticle. That one's the most efficient. That's total conversion. Okay. Off the course.